Hello everyone, welcome back to our NDT training session. I'm Mutlakmi Kanagaraj, quality expert. Today we are discussing about the skin effect. Let's start our session. First we are discussing the definition and behavior of the skin effect. When using AC alternating current, it flows through a metal. It does not spread evenly inside of the metal. Instead, the current moves mostly near the outer surface. So, the outer surface is meant the skin of the material. The faster the alternating current changes, that means higher frequency, the more tightly the current is pushed toward the surface. This reduces the penetration into the inside of the material. Why it is very important for magnetic particle testing means AC is best for surface cracks because the current stays on the surface, and the DC or half wave DC is better for subsurface defects because it penetrates very deep. So it is very important. The next point is higher current frequency is equal to shallower the penetration. This means the higher frequency alternating currents only travel along the surface layer. The next point is AC or pulsed currents primarily flow near the surface. This produces very high surface sensitivity, making them excellent for detecting surface breaking cracks or flaws. The next one is testing sequence. Performing DC or half wave DC first, then followed by AC testing. It ensures both surface and subsurface discontinuities. The first step is use DC or half wave DC. These currents penetrate deeper. They are effective in detecting subsurface discontinuities that may lie beneath the surface. The second step is follow with AC. After subsurface inspection, switch to AC test. AC provides high surface sensitivity. It ensures surface cracks, seams or laps are detected. This sequence maximizes flaw detection reliability. The next topic is demagnetization benefit. When we use alternating current for magnetization, its strength is often higher than DC. If we slow reduce the AC to 0 at the end of the inspection, the magnetic domains inside the material return to a random orientation. Already we saw a magnetic domains, how they are oriented, this process, and this is the process effectively demagnetizes the object, removing any residual magnetism left after the testing. The next topic is field distribution. In both long solid cylinders and hollow cylinders, whether magnetic or non-magnetic, the magnetic field is strongest at the outer face. As you move away from the surface, the field strength is decreased. This decrease follows the inverse square law, it meaning the strength reduces proportionally to the square of the distance. That means, example, if the magnetic field strength at 1 centimeter from the surface surface is 100 units. At 2 centimeter, it will reduce to about 25 units because 100 divided by 2 square is equal to 25. This is the concept, inverse square law. The next slide is, this image compares magnetic flux distribution inside two types of bars when magnetized. The first image shows a solid steel bar. This is a solid steel bar and this is a hollow steel bar. Both images show how DC and AC behave differently inside the metal. Let's discuss about the first image, that means solid steel bar. The graph shows a sharp peak at the surface. This is the outer edge, meaning the strongest magnetic flux density is always at the bar surface. So this is the surface, it shows a sharp peak. This is the outer edge. This is a AC current and this is a DC. In DC penetrates deeper into the bar. So flux is distributed more evenly across the cross section. This allows DC to detect both surface and subsurface flaws. And AC flux is concentrated only on surface, that is skin effect. Flux strength drops very quickly as you move inward. So the AC is highly sensitive for surface cracks but weak for subsurface discontinuities. This is the solid steel bar. The next one is hollow. The same peak at the surface. Again flux density is maximum at the outer surface. In DC current, flux penetrates throughout the hollow wall. This is the hollow wall. It provides good coverage both at the surface and deeper within the wall thickness. Here this is the deeper within the wall thickness. AC distribution, flux remains the concentrated only at the outer edge of the hollow cylinder. Inner walls receive very little flux from AC due to the skin effect. In both solid and hollow steel bars, the magnetic flux density B is highest at the outer surface of the bar. Whether the magnetizing current is DC or AC, the peak field strength always occurs at the bar surface. That means distance is equal to radius. The field strength drops inward from the surface toward the center. This is the solid bar or the inner wall. In a hollow bar, it is the inner wall. This happens because the enclosed current increases with radius. So the field lines are densest near the outside. I hope you are clear in this topic. So we will see the next video. Thank you.